Let me tell you something strange. Something so strange that the greatest physicists who ever lived argued about it for decades, lost friendships over it, wrote angry letters, stood up at conferences, and practically shouted at each other. And still, after almost 100 years, nobody has a satisfying answer. Here it is. When you watch a particle, it behaves differently than when you don't watch it. That's it. That's the whole mystery. And I know how that sounds. It sounds like something from a late-night philosophy session, or maybe something you'd hear from someone who's had a little too much coffee and started reading quantum physics blogs at 2 in the morning. But this isn't philosophy. This isn't speculation. This is one of the most rigorously tested, repeatedly confirmed facts in the history of science. When you set up a detector to observe what a tiny particle is doing, where it's going, which path it takes, the particle does something different than when you leave it alone. The simple act of looking changes the outcome. And as of right now, in this year, with all the technology and all the brilliant minds working on this problem, nobody on Earth can fully explain why. Let's start somewhere familiar. You've seen light before, obviously. You're probably lying somewhere right now where there's a lamp, or the glow of a screen, or maybe just the faint light from a hallway. That light is made of something. For a long time, people argued about what. Isaac Newton, back in the late 1600s, thought light was made of tiny particles. He called them corpuscles. Little bullets of light, shooting out from candles and stars and bouncing off things into your eyes. It was a pretty clean theory. It explained reflection nicely, and Newton was Newton, so people mostly went along with it. But there was this other idea. A Dutch physicist named Christian Huygens proposed, around the same time, that light was actually a wave, not a particle at all, a ripple, spreading outward, like when you drop a pebble into a still pond. And here's the thing, both ideas worked, sort of. Both could explain some of what light did, but they couldn't both be right. Light couldn't be a tiny bullet and a spreading wave at the same time. That would be like saying water is both wet and dry. You had to pick one. For about 100 years, Newton's particle idea won. Partly because it worked well enough, and partly because, well, Newton said it, and when Newton said something, people listened. But then, in 1801, a man named Thomas Young did something beautifully simple. He set up an experiment that would settle the argument once and for all. And what he found would eventually lead, through a chain of discoveries spanning 2 centuries, to the deepest, most unsettling mystery in all of physics. Young's experiment was elegant. He took a beam of light and aimed it at a barrier, with 2 thin slits cut into it. Behind the barrier, he placed a screen, just a flat surface where the light could land. Now, if light were made of particles, like Newton said, you'd expect a pretty simple result. The particles would fly through the 2 slits and hit the screen in 2 bright strips, one behind each slit, like spraying paint through 2 narrow openings. You'd get 2 bands of light, and that would be that. But that's not what happened. Instead, when Young looked at the screen, he saw something completely different. There were many bands of light and dark, alternating across the screen. Bright lines, dark lines, bright lines, dark lines. A pattern, and not just any pattern, an interference pattern. The exact kind of pattern you see when 2 sets of water waves overlap. When the peak of one wave meets the peak of another, they add up and you get a bigger wave, a bright band. When the peak of one meets the trough of another, they cancel out, a dark band. This was unmistakable evidence that light was behaving as a wave. The light going through one slit was interfering with the light going through the other slit, creating these alternating bands of reinforcement and cancellation. Young had done it. He'd shown that light was a wave, and for the next century, that was the answer. Light is a wave. Case closed. Textbooks were written, careers were built, and everyone moved on. Except the universe, as it turns out, wasn't finished being weird. Fast forward about 100 years to 1905. A young patent clerk in Switzerland, you might have heard of him, his name was Albert Einstein, published a paper that would change everything. Again, Einstein was looking at something called the photoelectric effect. Here's what that is. When you shine light on certain metals, the light knocks electrons off the surface, like tiny billiard balls being knocked loose. Now, if light were a wave, the energy should depend on how bright the light is, how much total wave energy you're sending in. But that's not what the experiments showed. What actually mattered wasn't the brightness, but the color, the frequency of the light. Dim ultraviolet light could knock electrons loose, but even the brightest red light couldn't. No matter how intense you made the red light, nothing happened. But even a faint beam of ultraviolet did the trick. Einstein's explanation was radical. He said light wasn't just a wave. It came in discrete packets, little bundles of energy. He called them quanta, and later they'd be called photons. Each photon carried a specific amount of energy determined by its frequency. High-frequency light, ultraviolet, had high-energy photons that could knock electrons loose. Low-frequency light, red, had low-energy photons that couldn't, no matter how many of them you sent. It wasn't the total amount of light that mattered. It was the energy per packet. So wait. Young proved light is a wave. Einstein proved light is a particle. They can't both be right, can they? This is where things start to get genuinely strange, because the answer, somehow, is yes. Both are right. Light behaves like a wave when you test it one way, and like a particle when you test it another way. And it's not that light is secretly one thing and just looks like the other under certain conditions. It genuinely, fundamentally, irreducibly behaves as both. This is wave-particle duality, and it's one of the cornerstones of quantum mechanics. When you first hear it, it sounds like a cop-out, like physicists just threw up their hands and said, "Fine, it's both." But it's deeper than that. It's telling us something profound about the nature of reality, something we're still trying to understand. Now, here's where our story really begins. Because wave-particle duality isn't just about light. It's about everything. In the 1920s, a French physicist named Louis de Broglie, and his name is pronounced de Broglie, in case you were wondering, proposed something audacious. He said if light, which everyone thought was a wave, can also act like a particle, then maybe particles, things like electrons, which everyone thought were definitely particles, can also act like waves. Matter waves, he called them. Every moving particle has a wavelength associated with it. This sounded ridiculous. An electron is a thing. It has mass. It sits in your atoms right now, orbiting nuclei, doing its job. How could it be a wave? But de Broglie did the math, and the math worked. He submitted this idea as his doctoral thesis, and the committee didn't know what to make of it. They were so uncertain that they sent it to Einstein for a second opinion. Einstein read it and reportedly said something like, "I believe it is a first feeble ray of light on this worst of our physics enigmas," which, coming from Einstein, was high praise. And then, a few years later, in 1927, two separate experiments, one by Clinton Davison and Lester Germer in the United States, and another by George Paget Thomson in Scotland, confirmed it. Electrons could diffract. They could create interference patterns. They could behave like waves. De Broglie was right. Particles, the solid little building blocks of matter, had a wave nature. Think about what that means. The atoms in your body, in your bones, in the hand you might be resting on the pillow right now. Every single electron in those atoms has a wavelength. You yourself have a wavelength, technically. It's incomprehensibly tiny, so small that it doesn't affect anything at your scale, but it's there. The math says so, and the experiments confirm it. Matter is wavy. Everything is wavy. The universe, at its most fundamental level, is made of something that's neither purely particle nor purely wave, but something else entirely. Something that doesn't have a name in everyday language, because everyday language was built for a world of solid objects and common sense, and quantum mechanics is neither. And this is the setup for the real mystery. Because once you accept that particles are also waves, the double-slit experiment stops being a neat demonstration about light and becomes something much more disturbing. Here's why. In the 20th century, physicists started doing the double-slit experiment not with beams of light, but with individual particles, one at a time. A single electron, fired at a barrier with two slits. And what happens is genuinely one of the most unsettling things in all of science. When you fire a single electron at the two slits, it hits the screen on the other side and makes a tiny dot, just one dot, like a particle. So far, so normal. You fire another electron, another dot, then another, and another. Each one lands in what seems like a random spot. If you only fired a few, you'd think the electrons were just particles, flying through one slit or the other and landing wherever they happen to land. But here's what happens if you keep going. If you fire thousands of electrons, one at a time, and you record where each one lands, something astonishing emerges. The dots, taken together, form a pattern. And not just any pattern, an interference pattern. The exact same pattern you'd get if waves were going through both slits and interfering with each other. Let that sink in. Each electron goes through the slits one at a time. There's only ever one electron in the experiment at any given moment. It's not bumping into other electrons. It's not interacting with a crowd. It's alone. And yet, somehow, it knows about both slits. Somehow, it's interfering with itself, as if each individual electron goes through both slits at the same time, interferes with itself like a wave, and then lands on the screen as a single dot, like a particle. That's already weird enough. But the truly mind-bending part, the part that has kept physicists up at night for almost a century, is what happens when you try to watch which slit the electron goes through. You'd think this would be straightforward. The electron goes through one slit or the other. It has to, right? It's a physical object, even if it's very small. So just put a detector at each slit. Watch which one the electron goes through. Mystery solved. And you can do this. Physicists have done this many times with extraordinary precision. You can place a tiny detector near each slit that registers whether an electron passed through it. You fire your electrons one at a time, and the detector tells you, this one went through the left slit, this one went through the right slit. Every electron goes through one or the other, just like you'd expect. But here's the thing. When you do this, when you watch which slit the electron goes through, the interference pattern disappears. It just goes away. Instead of the beautiful alternating bands of bright and dark, you get exactly what you'd expect from particles. Two clumps of dots, one behind each slit. No interference. No wave behavior. Just particles being particles. The electron was behaving like a wave, going through both slits, interfering with itself, producing that eerie pattern. But the moment you looked to see which slit it actually went through, it stopped doing that. It started behaving like a particle. As if the act of observation itself changed what the electron did. Think about what that means. Not observing, wave, interference pattern. The electron seems to go through both slits simultaneously. Observing, particle, two clumps. The electron goes through one slit or the other, like a normal object. The only difference between these two scenarios is whether or not you looked, whether or not information about the electron's path was available. And this is where almost everyone, including many physicists, gets that strange, uneasy feeling. Because this isn't supposed to happen. In the world we experience every day, watching something doesn't change what it does. If you set up a camera to watch a baseball fly through the air, the baseball doesn't suddenly change its trajectory. Observation is passive. You're just gathering information about something that's already happening. The thing does what it does, regardless of whether anyone is watching. But in the quantum world, the world of electrons, photons, atoms, and all the fundamental stuff that everything else is made of, observation is not passive. It's an active part of the story. The outcome literally depends on whether or not a measurement was made. And this isn't some subtle, marginal effect. It's the entire difference between a wave and a particle, between going through both slits and going through one, between an interference pattern and no interference pattern. Now, you might be thinking, well, okay, but doesn't the detector disturb the electron? Isn't this just a practical problem? The act of measuring bumps the electron and messes up its wave behavior? That's a perfectly reasonable thing to think, and it was, in fact, one of the first explanations people tried. The idea is sometimes called the disturbance theory of measurement. The detector interacts with the electron, gives it a little kick, and that kick is what destroys the interference. It's not observation per se that matters. It's the physical interaction required to make the observation. And there's some truth to this. At the quantum level, measuring something always involves interacting with it in some way. To detect an electron, you have to bounce a photon off it, or use an electromagnetic field, or do something that physically touches it. And yes, that interaction can disturb the electron. But here's the problem with this explanation. Physicists have gotten incredibly clever at minimizing the disturbance. They've designed experiments where the detector barely touches the electron. They've used techniques where the measurement is so gentle, so subtle, that the physical disturbance is negligible, and the interference pattern still disappears. More than that, and this is really the key, it's not the physical disturbance that kills the interference. It's the information. If the measurement records which path information, if it creates a record, anywhere in the universe, of which slit the electron went through, the interference pattern vanishes. Even if that information is recorded in a way that nobody ever actually looks at it. Even if you write the information down and then immediately throw it away, what matters is that the information exists. That's a very different thing from saying the detector bumped the electron. Let's sit with that for a second, because this is the heart of the mystery, and it's worth really letting it land. The interference pattern disappears not because the electron got physically disturbed, but because which path information became available. Information. Not force, not energy, not a physical push. Information. This is what makes the measurement problem in quantum mechanics so profound and so weird. It's not just a question about particles and waves. It's a question about the relationship between information, reality, and what it means for something to be observed. And nobody, not Niels Bohr, not Albert Einstein, not Richard Feynman, not any of the brilliant minds who've spent their careers working on this, nobody has come up with an explanation that everyone agrees on. There are interpretations. There are frameworks. There are mathematical formalisms that make correct predictions about what you'll measure. But there is no consensus on what's actually happening when you observe a quantum system. What physically occurs when a particle decides to be a wave or a particle. Why information about a particle's path should have any effect on how it behaves. Richard Feynman, one of the most important physicists of the 20th century, a man who won the Nobel Prize, who helped build the atomic bomb, who played the bongo drums and cracked safes for fun. Richard Feynman once said that the double-slit experiment contains the only mystery of quantum mechanics. He said that if you could explain this one thing, really explain it, not just describe the math but explain what's happening, you'd understand everything about quantum mechanics. And then he said, with characteristic bluntness, that nobody understands quantum mechanics. He wasn't being modest, he was being accurate. So let's go deeper. Let's look at how physicists have tried to make sense of this, because the attempts to explain the measurement problem have produced some of the strangest, most mind-bending ideas in the history of human thought. The first serious attempt to grapple with all this strangeness came from the people who invented quantum mechanics in the first place. In the 1920s, a group of physicists, centered in Copenhagen, Denmark, and led by Niels Bohr, developed what became known as the Copenhagen interpretation. This was the first attempt to answer the question, what does quantum mechanics actually mean? Bohr's answer was, in some ways, deeply unsatisfying, but it was also brilliant, and it dominated physics for half a century. Here's the essence of it. According to the Copenhagen interpretation, before you measure a quantum system, it doesn't have a definite state. The electron going through the double slits isn't secretly going through one slit or the other. It's genuinely in a superposition of going through both. It exists in a kind of blurred, overlapping state, described by what's called a wave function. The wave function encodes all the possible outcomes and their probabilities, but it doesn't pick one until a measurement is made. And then, when you measure, when you look, when you detect, when you observe, the wave function collapses. All those possibilities snap into a single, definite reality. The electron was in a superposition of left slit and right slit, and now it's definite. It went through the left slit. The wave function collapsed. This is the famous collapse of the wave function. And if you've heard of Schrödinger's cat, that poor imaginary cat in a box, simultaneously alive and dead until you open the box. That's what it's about. Before observation, multiple possibilities coexist. After observation, one becomes real. The act of measurement is what makes the transition from possibility to actuality. Now, this might sound reasonable enough, but think about what it's really saying. It's saying that the electron literally does not have a definite path until you check. It's not that you don't know which slit it went through. It genuinely went through both, in some sense, until the moment of measurement. Reality, at the quantum level, is not determined until it's observed. Bohr was okay with this. He argued that it was a mistake to ask what the electron is really doing between measurements. There is no really doing, he said. There's only what you can measure. Questions about the state of a system between measurements are, in his view, meaningless. The electron doesn't have a path between the source and the detector. It just has measurement outcomes. And the math, the wave function, is a tool for predicting those outcomes, not a description of some underlying reality. This is a radical philosophical position. It's essentially saying that reality, at the most fundamental level, doesn't exist in the way we normally think about it until someone looks. That observation is not just recording what's there. It's, in some sense, creating what's there. And some people were absolutely not okay with this. The most famous objector was Einstein, Albert Einstein, who had helped launch quantum mechanics with his 1905 paper on photons, spent the last 3 decades of his life arguing that quantum mechanics was incomplete. Not wrong, exactly. He acknowledged that the math worked brilliantly. But he insisted that there must be something deeper underneath, some hidden layer of reality that quantum mechanics was missing. The electron, he believed, must have a definite path. It must go through one slit or the other. The fact that we couldn't predict which one didn't mean it was random. It just meant we didn't know enough yet. Einstein's most famous objection is encapsulated in a phrase that's been quoted so many times it's practically a cliché, but it's worth hearing in context. He said, "God does not play dice with the universe." He wasn't making a religious argument. He was making a philosophical one. He believed, deeply, viscerally believed, that the universe was deterministic at its core, that everything happened for a reason, following definite rules. The idea that a particle could genuinely be in two places at once, and that observation could somehow collapse it into one, struck him as absurd. Bohr's response, by the way, was equally famous. Einstein, stop telling God what to do, which, you have to admit, is a pretty good comeback. The debate between Einstein and Bohr is one of the great intellectual dramas in the history of science. It played out over years, across multiple Solvay conferences. These were invitation-only gatherings of the world's top physicists, held in Brussels. The 1927 Solvay Conference is perhaps the most famous scientific meeting ever held. A photograph from that conference shows an astonishing collection of minds: Einstein, Bohr, Marie Curie, Max Planck, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Louis de Broglie, Wolfgang Pauli, Max Born, names that fill every physics textbook ever written. And at that conference, Einstein and Bohr went at it. Einstein would come to breakfast with a thought experiment, a hypothetical scenario designed to show that quantum mechanics led to a contradiction or an absurdity. And Bohr would go away, think about it all day, and come back at dinner with a resolution. Every single time, for years, Einstein would invent a clever new paradox, and Bohr would find a way out of it. It was intellectual combat at the highest level, and it forced both men, and all of physics, to think more deeply about what quantum mechanics really meant. But here's what's fascinating. Even though Bohr won every round, in the sense that he showed quantum mechanics was internally consistent, Einstein's objections pushed the conversation in ways that would prove profoundly important decades later. Einstein wasn't just wrong. He was wrong in the most productive possible way. In 1935, Einstein, along with two colleagues, Boris Podolsky and Nathan Rosen, published what might be the most important wrong paper in physics. It's known as the EPR paper, after their initials, and it proposed a thought experiment designed to prove that quantum mechanics was incomplete. Here's the idea, simplified. Quantum mechanics says that certain properties of particles, like their spin, are not determined until measured. An electron doesn't have a definite spin direction until you check. It's in a superposition of spin up and spin down simultaneously, and measurement collapses it into one or the other. Now, there's a phenomenon called entanglement, where two particles become correlated in such a way that measuring one instantly tells you about the other. If you create two entangled electrons and send them flying apart in opposite directions, their spins are linked. If you measure one and find its spin up, the other one will definitely be spin down, every time, without fail. Einstein's argument was this: the two particles fly apart. They're now far away from each other, maybe on opposite sides of a room, maybe on opposite sides of the galaxy. It doesn't matter. You measure particle A and find spin up. Instantly, with no time delay, you know particle B is spin down. But if particle B's spin wasn't determined until you measured particle A, then your measurement of A somehow instantaneously affected B. Information traveled between them faster than light, and nothing can travel faster than light. That's one of the bedrock principles of Einstein's own theory of special relativity. Einstein called this spooky action at a distance. He said it was absurd. His conclusion: the particles' spins must have been determined all along, from the moment they were created. There must be some hidden variable, some extra piece of information that quantum mechanics doesn't include, that predetermined the outcome. Quantum mechanics wasn't wrong, it was just incomplete. Like a weather forecast that predicts 50% chance of rain. The rain either happens or it doesn't, and the forecast's uncertainty is just ignorance, not a fundamental feature of reality. This was Einstein's position, and it was a perfectly reasonable one. For almost 30 years, it sat as an open question. There seemed to be no way to test whether quantum mechanics was genuinely random or whether there were hidden variables underneath. It was a philosophical difference, not an experimental one. And then, in 1964, a quiet, unassuming Irish physicist named John Stuart Bell changed everything. Bell did something that nobody thought was possible. He found a way to test whether Einstein was right. He showed that the predictions of quantum mechanics and the predictions of any hidden variable theory were actually different. Not just philosophically different, experimentally different. There were specific measurements you could make on entangled particles where quantum mechanics predicted one result and hidden variables predicted another. Bell wrote these differences down as a mathematical inequality, now called Bell's inequality, and said, "Go run the experiment. Nature will tell you who's right." The idea behind Bell's inequality is actually quite elegant, even if the math is technical. Here's the intuition. Imagine you have a pair of entangled particles, and you can measure each one's spin along different directions, say vertical, horizontal, or diagonal. Bell showed that if the particles have pre-existing hidden properties that determine their spin values in all directions, if Einstein was right, then the correlations between the measurements follow certain rules. They can only be so strong. There's a mathematical ceiling on how correlated the results can be. But quantum mechanics predicts stronger correlations than hidden variables allow. Quantum mechanics says the measurement results will be more tightly linked than any pre-existing hidden code could produce. And the difference is measurable. It's not subtle. It's clear-cut. Run the experiment, measure the correlations, and if they exceed Bell's limit, then hidden variables are out. Reality is genuinely indeterminate until measured, just like the Copenhagen interpretation says. Bell published his theorem in 1964, but it took years before technology caught up enough to run the experiment properly. The first serious test came in 1972 by John Clauser and Stuart Friedman at Berkeley. Their results violated Bell's inequality. Quantum mechanics was right, but the experiment had some technical loopholes, small gaps that a determined skeptic could exploit to argue the results weren't conclusive. The experiment that really settled the matter, or at least settled it to most physicists' satisfaction, came in 1982 by a French physicist named Alain Aspect and his team at the University of Paris-Sud in Orsay. Aspect designed an incredibly clever experiment that closed the most important loopholes. He used calcium atoms to produce pairs of entangled photons, and he set up the detectors so that the measurement direction was chosen randomly, at the last possible instant, after the photons were already in flight. This meant the particles couldn't have known in advance what was going to be measured. There was no way for information to travel between the two detectors fast enough to affect the results, and the result was unambiguous. Bell's inequality was violated, by a lot. The correlations were exactly what quantum mechanics predicted, and they exceeded what any hidden variable theory could explain. Einstein was wrong. Now, Let's be careful here, because Einstein was wrong deserves some nuance. Einstein was wrong about hidden variables. There are no secret, predetermined values hiding beneath quantum mechanics. When an electron's spin is unmeasured, it genuinely does not have a definite value. The universe is not a clockwork mechanism where everything is determined behind the scenes. The indeterminacy is real. But Einstein was right that something profoundly strange is going on with entanglement. When you measure one entangled particle and instantaneously affect the other, something is happening that defies our normal intuitions about space and separation. Quantum mechanics says no usable information is transmitted faster than light. You can't use entanglement to send a message, but the correlations are there, and they're stronger than any local, realistic theory can explain. The universe is, in some sense, more connected than it looks. Measurement here can be correlated with outcomes there, across arbitrary distances, with no apparent mechanism linking them. And this brings us back to our core mystery, but now with even more weight behind it. It's not just that watching a particle changes what it does. It's that the act of measurement, the creation of information about a quantum system, seems to be a fundamental part of how reality works. Not an add-on, not a side effect, a central mechanism. Something about the process of creating definite information from indefinite possibilities is built into the fabric of the universe, and nobody knows how. Let's talk about what happens when you try to push this mystery further, because physicists are nothing if not persistent. In the 1970s and 1980s, a physicist named John Archibald Wheeler, who, by the way, coined the terms black hole and wormhole, so he had a knack for evocative language. Wheeler proposed a thought experiment that made the measurement problem even stranger than it already was. Wheeler called it the delayed choice experiment. Here's the setup. Go back to the double-slit experiment. Normally, you decide before the experiment starts whether or not to put detectors at the slits. Detectors on, particle behavior, no interference. Detectors off, wave behavior, interference pattern. The choice of whether to observe determines the outcome. But Wheeler asked, what if you delay the choice? What if you wait until after the particle has already passed through the slits, after it's already decided whether to be a wave or a particle, and only then choose whether to measure which slit it went through? Now, if the particle had already committed to one behavior or the other, if it went through both slits as a wave or through one slit as a particle, then your late decision shouldn't matter. The particle already did what it did. You can't change the past. But quantum mechanics predicts something different. It says that even if you delay the choice until after the particle has passed the slits, your decision still determines the outcome. Choose to measure which path it took, and the data shows particle behavior. No interference, one slit. Choose not to measure, and the data shows wave behavior. Interference, both slits. As if the particle retroactively adjusted its behavior based on your future decision. Wheeler described this with a beautiful phrase. He said the past has no existence until it has been registered by a measurement in the present. The history of the particle, what it did, which slit it went through, whether it was a wave or a particle, is not settled until the measurement is complete. It's as if the particle's history is written backward, from the measurement to the source. And this isn't just theory. The delayed choice experiment has been performed multiple times, with increasing sophistication. In 2007, a team led by Vincent Jacques at the École Normale Supérieure in Paris did a version using individual photons and a setup where the choice of measurement was made truly randomly by a quantum random number generator after the photon had already entered the apparatus. The result confirmed Wheeler's prediction. The choice made after the photon entered the experiment determined whether it showed wave or particle behavior. Think about what that implies. The photon's behavior in the past depends on a measurement made in the future. Not in a science fiction, time travel kind of way. No information actually goes backward in time, but in the sense that the question, "What did the photon do?" doesn't have a definite answer until the measurement is complete. The past is not fixed until it's observed. Let's sit with that for a moment. In the world you and I experience, the past is the past. It happened, it's done. You ate dinner, or you didn't. The rain fell, or it didn't. History is written, and then it's over. But at the quantum level, history seems to be more like a story that isn't finished yet. The ending, the measurement, can determine what happened at the beginning, not by changing facts, but by bringing them into existence. If this doesn't make you slightly dizzy, you're not paying attention, and if it does make you dizzy, well, welcome to the club. You're in very good company. But it gets even stranger, because there's another experiment, a variation on the double slit, that takes the mystery of observation and measurement and pushes it to what feels like the breaking point of sanity. It's called the quantum eraser experiment. Here's the setup. You run the double slit experiment with entangled photon pairs. One photon, call it the signal photon, goes through the double slits and hits the screen. The other photon, the idler photon, goes off to a separate detector. Now, the idler photon carries information about which slit the signal photon went through. Because the two are entangled, measuring the idler can tell you the path of the signal. So what happens at the screen? No interference pattern. Because which path information exists, it's encoded in the idler photon. Even though nobody has looked at that information yet, its mere existence is enough to destroy the interference. But here's the twist. You can set up the idler photon's detector in two different ways. One way preserves the which path information. You can still tell which slit the signal went through. The other way erases it. You set up the detector so that the information about the signal photon's path is irretrievably lost. The idler photon is measured in a way that makes it impossible, even in principle, to determine which slit the signal went through. And when you erase the which path information from the idler, the interference pattern comes back. But here's the truly mind-bending part. In some versions of this experiment, the erasure of the which path information happens after the signal photon has already hit the screen. The signal photon has already landed. Its position is recorded. It's done. And yet, whether or not you erase the information from its entangled partner, a decision made later, determines whether the signal photon's data shows an interference pattern or not. To be precise, what actually happens is a bit subtler than that. And it's worth getting right, because this is one of those places where the popular science accounts sometimes get a little sloppy. If you look at all the signal photon data together, you always see a featureless blob, no interference pattern. The interference pattern is hidden. But if you sort the signal photon data into two groups, one group corresponding to idler photons where the which path information was erased, and another where it was preserved, then the erased group shows an interference pattern, and the preserved group shows no interference. The pattern was there all along, but it was hidden in the overall data, and only emerges when you correlate each signal photon with what happened to its idler partner. This means the data on the screen already contains both patterns, wave and particle, superimposed. Which one you see depends on how you choose to sort the data, and that choice can be made after everything has already happened. It's not that you're changing the past. It's that the past contains more information than you can see without knowing the future. And again, this has been confirmed experimentally. The most famous version was performed by Marlin Scully and his colleagues, building on theoretical work they published in 1982, and variations have been run many times since. The quantum eraser is real, it works, and it's telling us something profound about the role of information in physics. Now, at this point you might be feeling a bit overwhelmed, and that's completely fine. These ideas are genuinely difficult, not because they require advanced math. The concepts can be stated simply enough, but because they conflict with our deepest intuitions about how the world works. We grow up believing that things exist whether or not we look at them, that the past is fixed, that watching something doesn't change it. Quantum mechanics says all of these beliefs are, at the most fundamental level, wrong, or at least, they're not the whole story. And the question is, what do we put in their place? This is where the different interpretations of quantum mechanics come in. And this is where physics starts to shade into philosophy, which is something that makes some physicists deeply uncomfortable and other physicists absolutely giddy. Let's go through the main contenders, because they're all fascinating, and each one tells you something different about what kind of universe we might be living in. The Copenhagen interpretation, which we've already touched on, is the oldest and was for decades the default view. Bohr, Heisenberg, and their colleagues formulated it in the late 1920s, and it was the standard textbook answer for most of the 20th century. Its core claim is that the wave function is the complete description of a quantum system, and that it evolves smoothly and deterministically according to the Schrödinger equation, until a measurement is made. At that point, the wave function collapses, possibilities become actuality, and the question, what was the particle doing before the measurement, is, according to Copenhagen, not a meaningful question. There's a lot to admire about this interpretation. It's pragmatic, it works, it tells you how to calculate the probabilities, and those probabilities match experiments perfectly. If you're a physicist who just wants to get the right answer and move on to the next problem, Copenhagen is your friend. Shut up and calculate, as the physicist David Mermin put it, though he later said he was characterizing the attitude, not endorsing it. But there are deep problems with Copenhagen, and they've bothered people from the very beginning. The biggest problem is the measurement itself. Copenhagen says the wave function evolves smoothly until a measurement happens, and then it collapses. But what counts as a measurement? Where exactly in the chain of events does the collapse occur? The electron hits the detector. The detector produces an electrical signal. The signal is amplified. It's recorded by a computer. A human reads the screen. At which point did the wave function collapse? When the electron hit the detector, when the signal was amplified, when the human looked at the screen. This is called the measurement problem, and it's not a minor technical glitch. It's a gaping hole in the foundations of the theory. Copenhagen draws a line between the quantum world, where superpositions and wave functions reign, and the classical world, where things have definite properties and measurements produce definite outcomes. But it never tells you where that line is. It never defines what a measurement actually is, in physical terms. It's as if the theory works perfectly, but has a blank space right at its center, labeled, "Here a miracle occurs." The physicist John Bell, the same Bell who proved that hidden variables don't work, was deeply troubled by this. He once wrote, with characteristic dry wit, that the word measurement had no place in a fundamental theory. He said it should be replaced, at the very least, by experiment, but ideally by something more precise. You don't hear about the measurement problem in, say, electromagnetism or general relativity. Those theories describe what happens, period. They don't need a special role for an observer. Quantum mechanics, in its Copenhagen formulation, seems to need one, and that's strange. So people have proposed alternatives, lots of them, and the most radical, and perhaps the most elegant, was proposed in 1957 by a physics graduate student named Hugh Everett III. Everett's idea was simple in a way, and absolutely mind-blowing in its implications. He said, "What if the wave function never collapses? What if there is no measurement problem, because there is no collapse? What if the Schrödinger equation, the smooth, deterministic evolution of the wave function, is all there is?" This sounds great at first. No more mysterious collapse, no more undefined measurement, just one equation governing everything, all the time. But think about what it implies. If the wave function never collapses, then when you measure an electron and find its spin-up, the wave function doesn't collapse into spin-up. Instead, the wave function continues to describe both outcomes. You measured spin-up. But there's another branch of the wave function where you measured spin-down. And in Everett's interpretation, both branches are equally real. Both exist. In one branch of reality, you see spin-up. In another, you see spin-down. Every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. This is the many worlds interpretation. And yes, it means what you think it means. Every time a quantum event has multiple possible outcomes, and quantum events happen trillions upon trillions of times every second, in every atom in the universe, reality branches. There are, according to this interpretation, an incomprehensibly vast number of parallel universes, constantly multiplying, each one as real as this one. In some of them, you're lying in the same position right now, hearing these same words. In others, you made a different choice at some point today, or yesterday, or a billion years ago, when a cosmic ray hit an atom slightly differently, and everything diverged from there. Now, before you get too excited about parallel universes, or too alarmed, let me be honest about the status of this idea. The many worlds interpretation is mathematically clean. It solves the measurement problem by eliminating collapse entirely. It's deterministic. The wave function evolves smoothly forever. No randomness required. And it's taken seriously by a significant fraction of physicists. In some informal polls, not scientific surveys, but straw polls at physics conferences, many worlds has been gaining ground for decades. But it has its own problems. For one thing, it postulates an extraordinary amount of stuff, not just a few extra universes, an ever-branching tree of realities, multiplying at a rate beyond comprehension. If you thought the observable universe was big, many worlds makes it look like a grain of sand. And all those other branches are, by construction, completely unobservable from our branch. We can never see them, never interact with them, never test whether they're there. Which raises the question, if you can never test a theory, is it science? There's also the probability problem. In standard quantum mechanics, the wave function gives you probabilities. There's a 70% chance of this outcome, and a 30% chance of that outcome. But in many worlds, both outcomes happen with certainty. So where do probabilities come from? Why do we experience a world where outcomes happen with the right frequencies if every outcome actually occurs? This is called the Born rule problem, named after Max Born, who first proposed the probabilistic interpretation of the wave function. It's a genuine difficulty, and many worlds advocates have spent decades working on it. Some think they've solved it. Others are not convinced. And then there's a third major interpretation, one that takes a completely different approach. It's called the pilot wave theory, or de Broglie-Bohm theory, and it was first proposed by Louis de Broglie himself in 1927, the same de Broglie who proposed that particles have wavelengths, and then redeveloped independently by the American physicist David Bohm in 1952. The pilot wave theory says, particles are particles. They have definite positions at all times. They go through one slit, not both. There's no superposition, no collapse, no branching universes. The electron is always somewhere specific. But, and here's the twist, the particle is guided by a wave, a real, physical wave, the wave function, that exists in addition to the particle. The wave goes through both slits, creates an interference pattern, and then guides the particle along one path or another. The particle surfs the wave, like a cork bobbing on the surface of the ocean. The wave determines where the particle can go and how likely it is to end up in each place. In this picture, the interference pattern has a simple explanation. The guiding wave goes through both slits and interferes with itself, and the particle, surfing that wave, tends to end up in places where the wave is strong and avoids places where the wave is weak. If you put a detector at the slits, you disturb the wave, the interference pattern changes, and the particle behaves differently. No mysterious collapse, no observer effect. Just a wave being disturbed by a physical interaction. This sounds great, right? It's intuitive. It's deterministic. It preserves the common sense idea that particles are things with definite positions. Einstein, had he lived to see it fully developed, might have liked it, but it has its own issues. The guiding wave, in the pilot wave theory, is not a wave in ordinary space. For a system of two or more particles, it's a wave in a very high-dimensional space, called configuration space, where each particle's position adds dimensions. For a universe with trillions of particles, the wave function lives in a space with trillions of dimensions. That's not a minor mathematical abstraction. It means the guiding wave, the thing that's supposed to be the real physical entity, pushing particles around, exists in a space that bears no resemblance to the three-dimensional world we experience. Some physicists find this acceptable. Others find it deeply weird. You've solved the measurement problem, but you've introduced a cosmic wave function in an incomprehensibly high-dimensional space. Whether that's actually simpler than collapse is debatable. There's also the issue of non-locality. Bell's theorem showed that no local hidden variable theory can reproduce the predictions of quantum mechanics. The pilot wave theory is a hidden variable theory. It has definite particle positions. So how does it get around Bell's theorem? By being explicitly non-local. In the pilot wave theory, the guiding wave connects entangled particles instantaneously, regardless of distance. When you measure one entangled particle, the guiding wave everywhere updates instantaneously, affecting the other particle far away. This is the spooky action at a distance that Einstein hated. The pilot wave theory doesn't eliminate it, it embraces it. And this is the situation in quantum foundations today. You have Copenhagen, which works perfectly, but has a hole at its center. You have many worlds, which is mathematically elegant, but posits a staggering amount of unobservable reality. You have pilot waves, which are intuitive, but require a weird high-dimensional wave and explicit non-locality. And you have other interpretations too. There's QBism, which says quantum probabilities are subjective degrees of belief, not objective features of the world. There's relational quantum mechanics, proposed by Carlo Rovelli, which says quantum states are not properties of objects, but properties of the relationships between objects. There's the consistent histories approach, and the transactional interpretation, and objective collapse theories, like the one proposed by Roger Penrose, which ties the collapse of the wave function to gravity. Each one paints a different picture of reality. And here's the remarkable thing. As of right now, they all make the same experimental predictions. Every single one of these interpretations, when you work out the math, gives you the same numbers for every measurement ever made. They agree on what you'll see in the lab. They disagree, completely, fundamentally, irreconcilably, on what's happening behind the scenes, on what the universe is actually like when nobody is looking. This means the measurement problem is, in a real sense, an open problem in physics. Not because the math doesn't work. The math works brilliantly. Not because we can't make predictions. We can, with extraordinary precision. But because we don't know what the math means. We have the equations. We don't have the story. And that's a deeply unusual situation for physics to be in. Usually, when you have a theory that makes correct predictions, you also have a pretty good understanding of what the theory is saying about the world. General relativity tells you space-time curves. Electromagnetism tells you charges create fields. Thermodynamics tells you heat flows from hot to cold. These theories aren't just calculational tools. They're descriptions of reality. Quantum mechanics gives you the most accurate predictions in the history of science, and it can't tell you what's real. Let's go back to the double-slit experiment, because I want to dig into what's actually happening at the most granular level. We've talked about the big picture, interference patterns, wave-particle duality, the measurement problem, but there are details that make this even more fascinating, and they're worth dwelling on. When you fire a single electron at the double slits, where does it land? Quantum mechanics says you cannot predict exactly where. You can only give probabilities. The wave function of the electron, as it passes through the slits, spreads out and interferes with itself, creating a probability distribution, a map of where the electron is more or less likely to land. In the bright fringes of the interference pattern, the probability is high. In the dark fringes, it's 0 or near 0. But for any individual electron, you simply cannot know in advance where it will end up. And this isn't a limitation of your knowledge or your equipment. This is a fundamental feature of reality. Heisenberg's uncertainty principle, formulated by Werner Heisenberg in 1927, the same year as the Solvay Conference, says there are pairs of properties that cannot both be known precisely at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't about measurement technology. It's not that better instruments could overcome it. It's a fundamental limit built into the structure of the universe. Heisenberg was a young man when he figured this out, only 25 years old. He was working with Bohr in Copenhagen, and the story goes that the insight came to him during a late-night walk in a park. He was struggling with the question of what it means to observe an electron's position, and he realized that any observation would have to use light, photons, to illuminate the electron. But photons carry momentum, and when a photon bounces off an electron, it gives the electron a kick, changing its momentum. The shorter the wavelength of light you use, the more precisely you can see the electron, the more momentum the photon carries, and the bigger the kick. You can see the electron precisely, but you've changed its motion. Or, you can leave its motion undisturbed, but you can't see where it is. You can't have both. Now, modern physics understands the uncertainty principle more deeply than Heisenberg's original thought experiment suggests. It's not really about the act of measurement disturbing the particle, although that happens too. The uncertainty principle arises from the wave nature of matter itself. A wave that has a very well-defined position, like a sharp spike, doesn't have a well-defined wavelength, and wavelength is related to momentum. Conversely, a wave with a very well-defined wavelength extends over a large region of space and doesn't have a well-defined position. Position and momentum are complementary properties, connected by the mathematics of waves. You can't have a wave that's both a sharp spike and a smooth, extended oscillation at the same time. It's mathematically impossible. This is deep. It's telling you that the properties of a particle aren't like the properties of a billiard ball. A billiard ball has a definite position and a definite speed at every moment. An electron, in its quantum description, simply doesn't. Not because we can't measure both, because they don't both exist simultaneously. The question, where is the electron and how fast is it going, is, in some fundamental sense, a question without an answer. And this connects directly to the measurement problem. Because when you measure the position of an electron, you force it into a state of definite position, but you've made its momentum more uncertain. You've changed the state of the system by measuring it. The measurement is not passive. It reshapes the quantum state. And the more precise the measurement, the more dramatic the reshaping. Heisenberg and Bohr developed this into a broader principle called complementarity. The idea is that quantum objects have complementary aspects, wave-like and particle-like, position and momentum, time and energy, and no single experiment can reveal both simultaneously. You have to choose which aspect you want to see, and the choice of experiment determines which aspect appears. It's not that the object is secretly one thing and just looks like another. It's that the object is, in some genuine sense, both. But you can only ever see one face at a time. This is where Bohr's philosophy gets really interesting and really polarizing. Bohr argued that the properties of a quantum system don't exist independently of the experimental context. There's no way to talk about the electron's position without specifying how you're going to measure its position. The measurement setup is part of the phenomenon. You can't separate the observer from the observed. This might remind you of something from everyday life. Have you ever been in a conversation where someone's behavior changes depending on who's watching? Where the way you interact with someone affects what they do? In the classical world, that's psychology. In the quantum world, that's physics. The system and the measuring device are inextricably entangled, and I'm using that word deliberately, in a way that makes it impossible to describe the system as though the measurement didn't matter. Now, let me tell you about one more experiment that really drives the strangeness home. It's called the Elitzer-Vaidman bomb tester, and it was proposed in 1993 by Avshalom Elitzer and Lev Vaidman. It's one of the most beautiful thought experiments in quantum mechanics, and it has actually been realized in the laboratory with real optical components. Here's the setup. Imagine you have a collection of bombs. Some of them are live. They have a sensitive trigger that will go off if even a single photon hits it. Others are duds. Their triggers don't work. You want to identify which bombs are live without detonating them. In the classical world, this is impossible. The only way to test if the trigger works is to poke it. And if it works, the bomb explodes. Game over. But in the quantum world, there's a way. You set up an interferometer, essentially a more sophisticated version of the double-slit experiment, where a single photon can take two paths. Along one path, you place the bomb. Now, if the bomb is a dud, the photon takes both paths simultaneously. Because it's a wave, the paths interfere, and the photon always ends up at one particular detector. Always. 100% of the time. But if the bomb is live, something different happens. The bomb's trigger acts as a which path detector. If the photon goes along the bomb's path, the trigger detects it and the bomb explodes. If the photon goes along the other path, the trigger doesn't detect anything. But here's the quantum twist. Because the bomb is capable of detecting the photon, it constitutes a measurement of which path the photon took. And that measurement, even if the photon actually goes along the other path and never touches the bomb, destroys the interference. The result is that sometimes, about 25% of the time, in the simplest version, the photon ends up at a detector where it never would have gone if the bomb were a dud. And in those cases, you know the bomb is live, but it didn't explode. You detected the bomb without the photon ever touching it. You gained information about the bomb's state through what physicists call an interaction-free measurement. Think about that. You learned something about the bomb, that it's live, without anything actually interacting with it. The mere fact that the bomb could have detected the photon, even though it didn't, was enough to change the photon's behavior. The possibility of observation was sufficient to alter the outcome. This is the measurement problem at its most surreal. It's not just that observation changes what a particle does. It's that the possibility of observation, the existence of a path by which information could, in principle, be obtained, is enough. The particle responds not to what actually happens, but to what could happen. It responds to the potential for measurement, not just the measurement itself. And it gets better. Using a technique called the quantum Zeno effect, making many gentle measurements in rapid succession, you can push the detection probability toward 100%. The quantum Zeno effect, named after the ancient Greek philosopher famous for his motion paradoxes, says that measuring a quantum system frequently enough can freeze it in place. An unstable atom that would normally decay can be prevented from decaying by watching it often enough. The watched pot, at the quantum level, really doesn't boil. This has been experimentally confirmed. Frequent measurements can slow quantum transitions, and in the limit of continuous measurement, stop them entirely. And there's even a flip side, the anti-Zeno effect, where measurements can speed up evolution. The relationship between observation and quantum behavior is richer than a simple rule. Sometimes watching freezes things, sometimes it speeds them up, depending on the timing and the system. All of these experiments, the double slit, the delayed choice, the quantum eraser, the bomb tester, the Zeno effect, are telling us the same thing, from different angles. They're all pointing at this one deep truth. In quantum mechanics, the act of measurement, the creation of information about a system, is not a passive process. It's an active intervention in the physical world, and the rules governing how observation affects quantum systems are strange, counterintuitive, and still not fully understood. Let me take a step back here and talk about something that might help tie all of this together. One of the most important ideas in modern physics, one that's been slowly growing in influence over the past few decades, is the idea that information is fundamental. That information isn't just something we use to describe the physical world. It's part of the physical world, maybe the most basic part. This idea has roots that go back to the 1960s, when Rolf Landauer, a physicist at IBM, proposed that information is physical, not metaphorically, physically. Erasing a bit of information, Landauer showed, requires a minimum amount of energy and produces a minimum amount of heat. Information processing has thermodynamic costs. Information isn't abstract. It's inscribed in the physical world, in the configurations of atoms and fields, and manipulating it has real physical consequences. This connection between information and physics has grown deeper over the decades. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the surface area of their event horizon, not their volume, suggesting that the information content of a region of space is limited by its boundary, not its volume. This led to the holographic principle, proposed by Gerard 't Hooft and developed by Leonard Susskind in the 1990s. The deepest description of a three-dimensional region of space can be encoded on a two-dimensional boundary. The universe might be a hologram. This is still partly speculative, but the broader theme is not. Information is increasingly looking like it's at the center of physics, and this connects directly to the measurement problem. If information is physical, then measurement, the creation of information, is a physical process. Maybe the reason observation changes what a particle does is just the universe following its information processing rules. The physicist John Wheeler, the same one who proposed the delayed choice experiment, captured this idea in a famous phrase, "it from bit." He suggested that every physical quantity, every particle, every field, every force, derives its existence from information. The universe, he speculated, is fundamentally made of information, and physical reality is what you get when that information is processed, observed, and recorded. This is a radical idea, and not everyone agrees with it, but it's striking how many different lines of evidence, from quantum measurement to black hole thermodynamics, to the holographic principle, to the role of entanglement in spacetime, seem to converge on the same theme. Information isn't just what we know about the universe. It might be what the universe is made of, and if that's right, then the fact that observation changes quantum behavior isn't a paradox at all. It's a feature. It's what you'd expect in a universe where information is fundamental. Measurement creates information, and creating information changes the physical state. The mystery isn't that observation matters, it's that we ever expected it not to. But I want to be honest with you. This is one interpretation, one way of looking at it. It's a beautiful framework, and it has deep mathematical support, but it's not the final answer. Nobody has the final answer. That's what makes this topic so alive, so exciting. We're standing at the frontier. Let me tell you about decoherence, because this is another crucial piece of the puzzle, and it's one that's often misunderstood or glossed over. Remember the core mystery. A particle in isolation behaves like a wave, showing interference and superposition. But when you measure it, when you interact with it in a way that creates information about it, the wave behavior disappears, and it acts like a particle. The Copenhagen interpretation says this is because the wave function collapses. Many worlds says it's because the universe branches. Pilot wave theory says the guiding wave gets disturbed. But there's another way to approach this, and it's more practical and less philosophical. It's called decoherence. Decoherence is a physical process, not an interpretation. It's something that actually happens, that we can describe mathematically, observe experimentally, and even control in the laboratory. And it goes a long way toward explaining why quantum weirdness disappears at the scales of everyday life. Here's the idea. A quantum system, say an electron, exists in a superposition of states. It's in both states at once, described by a wave function that includes both possibilities. Now, when this system interacts with its environment, with air molecules, with photons of light, with the walls of the container, with anything at all, something happens to the superposition. The information about the quantum state leaks out into the environment. The electron becomes entangled with the air molecules. Its quantum state gets correlated with the states of countless environmental particles, and this entanglement, this spreading of information, causes the superposition to effectively disappear, not because the wave function collapses. The superposition is still there, in the mathematics, but it's been distributed across so many particles, the electron plus a billion air molecules, plus the photons that bounced off them, that it becomes, for all practical purposes, unobservable. The interference between the different parts of the superposition is washed out. It's like trying to hear a single conversation in a stadium full of people all talking at once. The signal is there, but it's buried in noise. This process, decoherence, happens incredibly fast. For a baseball, the time for quantum superposition to become unobservable is something like 10 to the minus 39 seconds. That's why you never see a baseball in two places at once. Not because quantum mechanics doesn't apply to baseballs, it does, but because the environment destroys the superposition almost instantly. Decoherence was developed primarily by H. Dieter Zeh in the 1970s and Wojciech Zurek in the 1980s. Zeh pointed out that the boundary between quantum and classical might not be fundamental at all, just a practical consequence of environmental interaction. Zurek developed these ideas rigorously, showing how decoherence selects pointer states that are robust against environmental entanglement, the states that look classical. Not because big things must behave classically, but because the environment constantly monitors them, selecting for definite positions, velocities, and properties. This is a beautiful insight. It explains why the classical world looks the way it does without introducing any mysterious collapse or any special role for consciousness or observation. The environment does the measuring. Air molecules are detectors. Photons of light are detectors. Every particle in your body is being constantly measured by the particles around it. You don't need a conscious observer to collapse a wave function. You just need interaction with the environment. And this feels like it should solve the measurement problem, right? Decoherence explains why big things behave classically. It explains why interference patterns disappear when particles interact with detectors. It explains why we never see cats in superpositions of alive and dead. So isn't the mystery solved? Well, not quite. And here's why. Decoherence explains why we don't see superpositions, but it doesn't explain why we see one particular outcome. Think of it this way. You measure an electron's spin. Before the measurement, it's in a superposition of spin up and spin down. After the measurement, decoherence ensures that the superposition is, for all practical purposes, gone. But it doesn't explain why you see spin up rather than spin down. The math, the full quantum description, including the environment, still describes both outcomes existing simultaneously. Decoherence separates them, makes them non-interfering, makes them effectively independent. But it doesn't eliminate one of them. It doesn't select a single outcome. In the many worlds interpretation, this is fine. Both outcomes exist, in separate branches. Decoherence explains why the branches don't interfere with each other. It's the mechanism that makes many worlds consistent with our experience of a single, definite reality. In the Copenhagen interpretation, decoherence narrows the problem but doesn't solve it. It shows where the quantum classical boundary effectively is. It's wherever decoherence kicks in, but it still needs collapse to select one outcome. In the pilot wave theory, decoherence helps explain why the guiding wave effectively behaves classically for large objects. But the particle always has a definite position anyway, so the problem is already solved differently. So decoherence is a crucial piece of the puzzle. It bridges the gap between quantum and classical. But it doesn't, by itself, resolve the fundamental question. It doesn't tell you what really happens when a measurement is made. It doesn't explain why, from your perspective, the world has definite properties, instead of existing as a vast superposition of all possibilities. And that question, why does the world look definite when the math says it should be a superposition, remains open. Now, there's one more angle I want to explore, because it connects the measurement problem to something even deeper, something about the nature of reality itself. In the 1990s and 2000s, physicists started asking a question that sounds deceptively simple. What is a quantum state? Is the wave function a description of reality, a literal map of what exists, or is it just a tool for making predictions? Is it ontic, in the philosophical jargon, or epistemic, If the wave function is ontic, if it's real, then a particle in a superposition of two positions is genuinely, physically in both positions simultaneously. That's what many worlds take seriously. That's what Schrödinger's equation describes. Reality is the wave function, and the wave function says multiple things are true at once. If the wave function is epistemic, if it's just a representation of your knowledge or beliefs about the system, then a particle in a superposition isn't really in two places. You just don't know which place it's in. The superposition reflects your ignorance, not the particle's reality. This is more in the spirit of QBism, quantum Bayesianism, developed by Christopher Fuchs, Carlton Caves, and Rudiger Schack. In QBism, quantum probabilities are personal, subjective judgments about what you'll experience if you make a measurement. The wave function is a tool for organizing your expectations, not a picture of the world. In 2012, a result known as the PBR theorem showed that, under reasonable assumptions, the wave function cannot be purely epistemic. It must be, at least in part, a description of reality. This shifted the conversation significantly. If the wave function is real, then the measurement problem is not just about our knowledge, it's about the world. Particles genuinely exist in superpositions. Measurement collapses real superpositions into definite states. Measurement changes reality, not just your description of reality. Reality. If you've been lying there thinking this all sounds too weird to be true, you're not alone. Physicists have felt that way for 100 years. The mathematics is not in question. The predictions are not in dispute. What's in dispute is the story. What's happening? What it means. Let me bring in one more thread. Because the story of quantum measurement doesn't stop with photons and electrons. It extends to the macroscopic world in ways that are becoming increasingly important. In the past 2 decades, physicists have managed to put larger and larger objects into quantum superpositions, not just individual atoms, molecules, complex molecules with dozens of atoms. In 1999, Anton Zeilinger and his team at the University of Vienna demonstrated interference with carbon-60 molecules, buckyballs, those soccer ball-shaped molecules made of 60 carbon atoms. These are large by quantum standards. They're visible under an electron microscope, and yet, when fired at a double slit, one at a time, they produced an interference pattern. They went through both slits. A molecule that you could, in principle, see with the right equipment was behaving like a wave. Since then, experiments have pushed the boundary further. In 2019, a team led by Marcus Arndt, also in Vienna, demonstrated interference with molecules made of over 2,000 atoms, the largest objects ever to show quantum behavior. These molecules are enormous by quantum standards. They have measurable sizes and masses, and yet they still produce interference patterns when isolated from their environment. This matters because it tells us that there's no size limit, at least no clear size limit, where quantum mechanics stops working. The transition from quantum to classical isn't a hard boundary. It's a gradual transition driven by decoherence. The bigger the object, the faster it decoheres, the harder it is to maintain a quantum superposition. But in principle, the quantum rules apply all the way up. There's no known point where the Schrödinger equation stops being valid. Which raises an uncomfortable question. If quantum mechanics applies to everything, then what about the measuring device? The detector is made of atoms. Those atoms obey quantum mechanics. When the detector interacts with the electron, the detector enters a superposition, and the amplifier, and the computer, and you. One branch of you sees left slit, and another branch sees right slit. This is the von Neumann chain. John von Neumann showed in 1932 that you can place the cut between quantum and classical anywhere, at the detector, the amplifier, the observer, and get the same predictions. The math doesn't care where you draw the line, which means the theory itself doesn't tell you where measurement occurs. The quantum world is all there is. The classical world is an approximation, emerging from decoherence, and the measurement problem, in its deepest form, becomes, why do we experience a single definite outcome? If the math says everything is a vast superposition, and decoherence separates the branches without eliminating them, why does it feel like only one thing happens? This is, arguably, the hardest question in physics, about the things we observe every moment and our inability to explain why observation works the way it does. Let me tell you about Schrödinger's cat, because it deserves more than a passing reference. The thought experiment is famous, but often misunderstood. Schrödinger wasn't proposing a cool mystery about cats. He was pointing out something he considered absolutely absurd about quantum mechanics, using the cat to make the absurdity impossible to ignore. It's 1935, and Schrödinger is deeply uncomfortable with the Copenhagen interpretation. He designs a thought experiment to show that quantum mechanics, taken at face value, leads to something ridiculous. Put a cat in a sealed box. Inside the box, there's a tiny piece of radioactive material, a Geiger counter, a vial of poison gas, and a mechanism that connects them. If the radioactive atom decays, which is a quantum event, genuinely random, described by a wave function, the Geiger counter detects it, triggers the mechanism, breaks the vial, and kills the cat. If the atom doesn't decay, the cat lives. Now, according to quantum mechanics, the radioactive atom, before measurement, is in a superposition of decayed and not decayed. Both states coexist, but the atom is connected to the Geiger counter, which is connected to the mechanism, which is connected to the cat. So if you follow the quantum logic all the way up, the cat should be in a superposition of alive and dead. Both states coexist. Until you open the box and look. Schrödinger's point was, this is crazy. A cat cannot be both alive and dead. The fact that quantum mechanics seems to imply this means something is wrong, or at least incomplete, about the theory. The cat is the reductio ad absurdum. It's the argument that shows the Copenhagen interpretation can't be right, at least not without some modification. But here's the funny thing. Over the decades, the thought experiment that Schrödinger intended as a criticism of quantum mechanics has become its most iconic illustration. Pop culture embraced the half-alive, half-dead cat as a symbol of quantum weirdness, rather than as a sign that something was broken. And depending on which interpretation of quantum mechanics you subscribe to, the cat's status is different. In the Copenhagen interpretation, the cat is in a superposition until someone opens the box and looks. Then the wave function collapses, and the cat is either alive or dead. In many worlds, the cat is in a superposition, and when you open the box, the universe splits. In one branch you see an alive cat, in another you see a dead cat. Both are real. In the pilot wave theory, the radioactive atom always had a definite state. It either decayed or it didn't, and the cat was always definitely alive or definitely dead. The uncertainty was in your knowledge, not in reality. And decoherence offers a fourth perspective, the cat. Being made of trillions of atoms interacting with the environment constantly, decoheres almost instantly. The superposition of alive and dead effectively vanishes in a fraction of a femtosecond. You'd never observe the superposition, not because it doesn't exist mathematically, but because it becomes observationally invisible almost immediately. The cat is, for all practical purposes, either alive or dead well before you open the box. It just takes a measurement to tell you which. Each interpretation handles the cat differently. None of them are obviously wrong, and that's the state of affairs. But let me come back to something more personal, more intimate, because the measurement problem isn't just a puzzle for physicists to argue about at conferences. It touches on questions that human beings have been asking for millennia. What is real? Does the world exist when nobody's looking? Is there an objective reality out there, independent of our observations? Or is reality somehow dependent on, even created by, the act of perception? These are ancient questions. Philosophers have debated them for thousands of years, but quantum mechanics makes them uncomfortably scientific. It's no longer just philosophy to ask whether the moon exists when nobody is looking. Einstein reportedly asked this very question, in frustration, to illustrate how absurd the Copenhagen interpretation seemed. He asked Abraham Pais, a fellow physicist, whether he believed the moon was there when nobody was looking at it. The implication was, of course it is. Don't be ridiculous. But Bohr's answer, and this captures the depth of the disagreement, would have been something like, the moon exists in the way that a very large, very thoroughly observed, very completely decohered quantum system exists. It's there because it's constantly interacting with photons, with gravity, with everything around it. It's been measured, in the broadest sense, by the entire universe, continuously, for billions of years. So yes, the moon is there, but not because reality exists independently of observation, because the moon has been observed, in the quantum sense, without interruption since it formed. And this is where it gets very subtle, and where even physicists start to disagree about what words mean, which is always a sign that something important is at stake. Let me take another detour, and a pleasant one, to talk about quantum computing. Because quantum computing is, in a very real sense, an attempt to exploit the measurement problem, to use the weirdness of quantum superposition before measurement collapses it, to do useful work. A classical computer stores information in bits, ones and zeros. A quantum computer uses qubits, which can be in a superposition of 1 and 0 simultaneously. 2 qubits can represent 4 states at once. 3 qubits, 8 states. A quantum computer with 300 qubits can represent more states simultaneously than there are atoms in the observable universe. And while those qubits are in superposition, before measurement, quantum operations can act on all those states at once. That's where the power comes from. But here's the catch. You can only access the result through measurement, and measurement collapses the superposition. You get one answer, not all of them. The entire art of quantum computing is designing algorithms that choreograph the interference, making wrong answers cancel out and the right answer stand tall, so that when the collapse happens, it gives you what you want. And building a quantum computer is brutally hard, precisely because of the measurement problem. The environment is constantly trying to measure your qubits. Every stray photon, every thermal vibration is a potential measurement that could collapse the superposition and ruin the calculation. Quantum computing is a race against decoherence, superconducting circuits cooled to thousandths of a degree above absolute zero, individual atoms trapped by lasers, photons threaded through optical fibers with exquisite precision, all of it designed to exploit quantum superpositions while keeping the environment from collapsing them. If we truly understood the measurement problem, what happens when a quantum system is measured, and how to control it, quantum computers would be much easier to build. The measurement problem is not an abstract philosophical curiosity. It's a practical barrier to one of the most powerful technologies imaginable. Let me tell you one more story about the human side of this, because the history of the measurement problem is not just a story of ideas. It's a story of people. brilliant, stubborn, passionate people who fought about these ideas with an intensity that borders on obsession. Niels Bohr was, by all accounts, an extraordinarily kind man, except on the subject of quantum interpretation, where he was immovable. When Einstein raised objections, Bohr worked himself into states of intense anxiety, pacing and muttering until he found the resolution. His health suffered. The intellectual stakes were that high. Einstein, on the other side, spent the last 3 decades of his life searching for a deeper theory. He never found it. When he died in 1955, many physicists considered his objections the unfortunate hobby of a once great mind. But history has been kinder to Einstein. The questions he raised about entanglement, hidden variables, the meaning of measurement, turned out to be profoundly important. Bell's theorem, aspects experiment, quantum computing, all grew from the seeds Einstein planted. His wrong ideas were more productive than many people's right ones. And then there's Hugh Everett, whose story is particularly poignant. Everett proposed many worlds in 1957 as his PhD thesis at Princeton. Bohr's circle dismissed it. The reaction was so cold that Everett left physics entirely, going into military and business consulting. He never returned to quantum foundations. Everett died in 1982, at 51, largely forgotten by the physics community. It was only decades later that many worlds gained traction. Today, he's recognized as a brilliant thinker whose work was decades ahead of its time. But he never lived to see that recognition. Everett asked, "What if the wave function never collapses? What if it's all real?" His era said, "Absurd." Now, a significant fraction of physicists think he might have been right. David Bohm's story runs parallel. He developed the pilot wave theory in 1952, but during the McCarthy era, he was hauled before the House Un-American Activities Committee, arrested, and effectively blacklisted from American academia. He spent the rest of his career in Brazil, Israel, and England. His theory was ignored for decades, dismissed as a curiosity, overshadowed by Copenhagen's dominance. He died in 1992, before the revival of interest in his ideas. These stories matter because the measurement problem isn't just an intellectual puzzle. It's a deeply human story. The people who grappled with it were driven by the same curiosity you might feel right now. They wanted to know what reality is, and they were willing to sacrifice their careers, their reputations, and their peace of mind to find out. Let me take you somewhere unexpected now. Let's talk about consciousness, because it's impossible to discuss the measurement problem in quantum mechanics without eventually bumping into the question of consciousness and whether it plays any special role. The idea that consciousness causes wave function collapse has a surprisingly long pedigree in physics. It was first suggested, in a somewhat guarded way, by John von Neumann in his 1932 treatise on the mathematical foundations of quantum mechanics. Von Neumann showed that in the chain of measurement, particle, detector, amplifier, computer, observer, the collapse could be placed anywhere. The math worked no matter where you drew the line. But he also noted that the one place where the chain necessarily ends, the one place where you can't push the collapse any further down the road, is the conscious observer. You can describe the detector as quantum, the amplifier as quantum, the computer as quantum. But at some point, there's a mind looking at the result, and that mind experiences a single, definite outcome. Maybe that's where the collapse happens. This idea was picked up and championed by Eugene Wigner, a Nobel Prize-winning physicist and one of the great mathematical minds of the 20th century. Wigner proposed a thought experiment that extends Schrödinger's cat. Imagine a friend of Wigner's friend, who performs a quantum measurement inside a sealed laboratory. From the friend's perspective, they make the measurement and see a definite result. The wave function has collapsed, as far as they're concerned. But from Wigner's perspective, outside the lab, the friend and the quantum system are both inside a sealed box, like Schrödinger's cat, and they should be in a superposition until Wigner opens the door and looks. So, who's right? Has the wave function collapsed, or hasn't it? The friend says, yes. Wigner says, not yet. This is called Wigner's friend paradox, and it's one of the sharpest formulations of the measurement problem. It shows that if collapse depends on observation, then whose observation counts? When does the collapse happen? When the friend looks, or when Wigner looks at the friend? Wigner himself believed, at least for a time, that consciousness was the key ingredient, that the wave function collapses when a conscious mind becomes aware of the result. This is a metaphysically bold claim. It puts consciousness, human awareness, at the center of physics, as a fundamental ingredient in how reality works. Most physicists today are uncomfortable with this idea, and for good reason. It raises enormous questions. What counts as consciousness? A human brain, sure, but what about a chimpanzee, a dog, a fruit fly, a bacterium? Where do you draw the line? And why should the laws of physics depend on biology? The equations of quantum mechanics don't contain anything that says, and then a conscious mind looks. There's no term in the Schrödinger equation for awareness or perception or subjective experience. Consciousness, in the physics, is conspicuously absent. Decoherence, as we discussed, largely resolves this without invoking consciousness. The superposition effectively disappears, for practical purposes, as soon as the quantum system interacts with its macroscopic environment. You don't need a mind to collapse the wave function. You just need interaction with a complex environment. An air molecule will do the job. But, and this is a subtle but, decoherence doesn't fully resolve Wigner's friend. It explains why the friend sees a definite outcome, decoherence inside the lab, but it doesn't resolve the question of whether Wigner, outside the lab, should describe the friend's state as definite or superposed. In many worlds, both descriptions are valid. The friend is in both states, in different branches. In Copenhagen, the friend's measurement caused a collapse, and Wigner just doesn't know the result yet. In Cubism, both Wigner and his friend have their own quantum descriptions, and neither one is more real than the other. Recently, physicists have started to experimentally probe Wigner's friend scenarios. In 2019, a team at Heriot-Watt University in Edinburgh used entangled photons to simulate a situation where observers make measurements inside sealed boxes, while external observers measure the boxes. The results were consistent with quantum mechanics, but inconsistent with the assumption that the inner observers had definite outcomes before the outer ones looked. The measurement problem is not just a thought experiment anymore. It's being probed in the laboratory, and the results suggest the textbook story is not the whole truth. Let me widen the lens a bit more, because the measurement problem in quantum mechanics doesn't exist in isolation. It connects to other deep mysteries in physics, and some of those connections are surprisingly intimate. One of the biggest unsolved problems in physics is how to reconcile quantum mechanics with general relativity. Quantum mechanics describes the very small, atoms, particles, fields. General relativity describes the very large, stars, galaxies, the curvature of space-time. Both theories work spectacularly well in their own domains, but they're fundamentally incompatible. Quantum mechanics assumes a fixed, flat space-time as a background stage on which particles dance. General relativity says space-time is dynamic. It bends, stretches, and curves in response to mass and energy. Merging the two, creating a theory of quantum gravity, has been the holy grail of physics for nearly a century, and the measurement problem is right there, at the intersection. Roger Penrose, who won the Nobel Prize in 2020, has proposed that the collapse of the wave function is caused by gravity. When a quantum superposition involves states that curve spacetime differently, Penrose argues, gravity itself destabilizes the superposition and forces it to collapse. For an electron, the gravitational difference is negligible, so quantum superpositions persist. But for a large object, the gravitational difference is enormous, and collapse happens in fractions of a femtosecond, consistent with why we never see cats in superpositions. The beautiful thing is that Penrose's proposal is testable. It predicts a specific relationship between mass, spatial separation, and collapse timescale. Experiments are being designed to test this, though they're extraordinarily difficult. But the fact that the measurement problem might be connected to gravity, that observation might be linked to space-time, is one of the most exciting possibilities in modern physics. There's another connection worth mentioning. In 2013, Juan Maldacena and Leonard Susskind proposed an extraordinary conjecture, ER equals EPR. They suggested that wormholes, tunnels through space-time, and quantum entanglement might be the same thing. Every pair of entangled particles, they proposed, is connected by a tiny wormhole. If this is right, the fabric of space-time itself might be woven from quantum entanglement. Space and time might not be fundamental. They might emerge from a deeper quantum description. And the measurement problem sits at the heart of this, because measurement creates entanglement between the system and the observer. If entanglement is related to the structure of space-time, then observation might be related to the formation of space-time itself. This is speculative, very speculative, but thrilling, in a quiet, bedtime sort of way. The idea that when you watch a particle, you're not just gathering information, you're participating in the construction of reality. Let me bring in one more thread before we start bringing this all together. I want to talk about something called weak measurement, because it adds yet another dimension to the mystery. In a normal, or strong, quantum measurement, you learn the exact value of some property. You measure an electron's spin and get up or down. The wave function collapses to the measured state. The system is fundamentally changed. But in a weak measurement, you barely interact with the quantum system. You extract only a tiny amount of information, not enough to collapse the wave function, not enough to determine the state definitively, just a whisper of information, a hint. Weak measurements were developed theoretically by Yakir Aharonov, David Albert, and Lev Weidman in 1988. And they've opened up an entirely new way of exploring quantum mechanics. Because here's the thing, weak measurements don't collapse the wave function. They don't destroy the superposition, and yet they still give you information, noisy, uncertain information, but real information, about what the system is doing between strong measurements. And some of the results from weak measurements have been genuinely surprising. In certain experimental setups, weak measurements seem to indicate that particles take strange, unexpected paths through interferometers. They've been used to observe the average trajectories of photons in a double-slit experiment, and the trajectories look remarkably like the paths predicted by Bohm's pilot wave theory. The photons seem to follow smooth, well-defined paths, curving around the slits and converging where the interference pattern is bright. Now, this doesn't prove that pilot wave theory is correct. Weak measurements don't reveal the path of individual particles. They give averages over many runs, and the interpretation of those averages is still debated. But it's remarkable that a measurement technique can give us a glimpse, however fuzzy, of what particles are doing between measurements, without collapsing the wave function and destroying the very behavior we're trying to observe. It's as if weak measurement lets you peek behind the curtain, just a little, without disturbing the show. You don't see the full picture. You see shadows, outlines, suggestions. But even those glimpses are more than we thought possible, and they're adding new dimensions to the measurement problem. In 2011, Ephraim Steinberg's team at the University of Toronto used weak measurements to reconstruct the average trajectories of photons in a double-slit experiment. The trajectories showed photons following smooth, flowing paths, like a river splitting around a rock and rejoining, weaving together to form the interference pattern. Whether these trajectories are real depends on your interpretation. In Copenhagen, there are no trajectories between measurements. In pilot wave theory, they're exactly what the theory predicts. Even this remarkable experimental advance doesn't resolve the measurement problem. It adds new perspectives. But the mystery remains. So let's come back to where we started. Let's come back to that core question, the one that's been pulling us forward this whole time. Why does watching a particle change what it does? You know more now than you did at the beginning. You know about the double-slit experiment, how particles create interference patterns when unobserved, like waves passing through both slits at once, and how those patterns disappear the moment you set up a detector to watch which slit they go through. You know about wave-particle duality, how everything in the universe, from photons to electrons to molecules of astonishing complexity, behaves as both a wave and a particle, depending on how you look at it. You know about the Copenhagen interpretation, with its mysterious wave function collapse, and the measurement problem that sits like a crack in its foundations, the undefined boundary between the quantum and the classical, the unanswered question of what counts as a measurement. You know about many worlds, with its dizzying proliferation of branching realities, every quantum event splitting the universe into copies, all equally real, none accessible from the others. You know about pilot waves, guiding particles along definite paths, determined by a wave that fills the universe in a space too vast to visualize. You know about Bell's theorem, which proved that the universe is stranger than Einstein wanted it to be, about Aspect's experiment, which showed that entangled particles are correlated more strongly than any local, realistic theory can explain, about delayed choice experiments, where the past seems to depend on measurements made in the future, about quantum erasers, where information created and then destroyed can restore patterns that had been obliterated, about the Elitzer-Vadman bomb tester, where the mere possibility of observation, even when nothing is actually observed, changes the outcome. You know about decoherence, that beautiful bridge between quantum and classical, showing how the environment monitors everything, selecting for classical-looking states while burying quantum superpositions in noise. And you know that decoherence, for all its explanatory power, doesn't fully resolve the measurement problem. It shows why we don't see superpositions, but it doesn't explain why we see one particular outcome rather than another. You know about the human stories, about Bohr and Einstein, arguing across years and conferences, each pushing the other to think deeper, about Everett, whose radical idea was dismissed in his lifetime and celebrated after his death, about Bohm, exiled by politics and ignored by physics, whose pilot wave theory gained respect only decades later, about Schrödinger's cat, designed as a criticism and embraced as an icon, about Bell, quiet and precise, whose theorem changed the landscape of physics. And through all of it, running like a thread through the whole tapestry, is this one astonishing, undeniable, experimentally confirmed fact. The act of observation changes the behavior of quantum systems, not as a side effect, not as an artifact of clumsy measurement, as a fundamental feature of how the universe works. So why? Why does watching a particle change what it does? And here's the honest answer. The answer that the best physicists in the world would give you if you caught them in a quiet moment, late at night, after the conference talks were over and the formality had dropped away. We don't know. We have descriptions. We have interpretations. We have mathematical frameworks that predict, with stunning accuracy, what we'll see when we look. But we don't have an explanation. We don't have a story that everyone agrees on. We don't know what's happening beneath the math. And that's not a failure. That's the frontier. Think about it this way. For most of human history, we had no idea what light was. Then we figured out it was a wave. Then we figured out it was also a particle. Then we discovered that everything is both. Then we found that observation plays a role in determining which aspect appears. Each answer opened up deeper questions. Each layer of understanding revealed another layer of mystery. That's how science works. Not by reaching a final answer, but by asking better questions. The measurement problem isn't a dead end. It's the most important open door in physics. On the other side of that door might be a new understanding of reality, one that's as different from quantum mechanics as quantum mechanics is from classical physics, one that explains what observation really is, what the wave function really describes, and why the universe seems to care whether or not anyone is watching. Some physicists think the answer lies in quantum gravity, that the marriage of quantum mechanics and general relativity will naturally resolve the measurement problem. Others think it lies in information theory, that the universe is fundamentally a structure of information, and measurement is just information processing. Others think we need a completely new framework, something nobody has thought of yet. And maybe, just maybe, the answer is even stranger than any of these possibilities. Maybe the measurement problem is telling us something about the nature of existence that we don't yet have the language or concepts to understand. Something that will require not just new physics, but new ways of thinking about what physics is. The universe, at its most fundamental level, is not made of matter. It's not made of energy. It might be made of information, or of mathematics, or of something we don't have a word for. And whatever it's made of, it has this one remarkable property. It responds to being watched. It changes when observed. It behaves differently when information about it is created. That same force, the same quantum mechanics that makes particles change their behavior when you look at them, is happening right now, all around you, all the time. In every atom of the pillow under your head, in every photon of whatever faint light is still reaching your eyes, in every electron, in every molecule of the air you're breathing. The quantum world isn't somewhere else. It's here. It's everything. It's you. And nobody can explain why watching it makes it change. Not yet, but somebody will. Somewhere, right now, a physicist is lying awake. Maybe not so differently from the way you're lying right now, turning this problem over in their mind, looking for the crack in the wall, the thread that, if pulled, might unravel the whole mystery. Maybe they'll find it tomorrow. Maybe it'll take another 100 years. But the question is too beautiful, too important, too fundamental to remain unanswered forever. For now, it's enough to know that you live in a universe that's stranger and more wonderful than anyone could have imagined. A universe where the simple act of looking changes what you see, where the boundary between the observer and the observed is blurred, maybe even non-existent, where the past is not fixed, the future is not determined, and reality itself seems to hang in the balance until someone, somewhere, asks a question and gets an answer. That's the universe you're falling asleep in tonight, A universe of open questions and quiet wonder. A universe that changes when you watch it, and nobody can explain why. But isn't that, in its own strange, beautiful way, the most wonderful thing of all?